an idea. So if you know the temperature and you know the CV, you can find what is your internal energy or specific internal energy. U square by 2, U comes from the velocity, macroscopic velocity of the chunk, okay, not the molecular translation velocity or something. So all that molecular description is taken into account in that first small u. U square by 2 gives you the macroscopic velocity of that infinitesimal chunk. And g times z, essentially g is the acceleration due to gravity and z is the, the height in the vertical direction. So it's just by choice of convention. That gives you the potential energy per unit mass, because potential energy is given by mgh. In this case, z is our h direction, and when you do mgh per mass, so essentially you end up with gh, in this case gz. Now comes a very important consideration. Okay, so on the left hand side, we once again write q dot minus w dot shaft, but we bring this pressure work on the right hand side, and something very important happens. What is happening here is, now we have, so say if you look at this, so the pressure work involves integration of pressure times elemental area times the velocity component in the direction of the normal to that elemental area. However, this integration is on the control surface, and this one integration is also on the control surface, and you see that here also we have the similar u dot n dA on both these integrations. So what happens is, we can actually bring this P inside a common integral over the surface of the control volume. So you see what we have done is, so we have just put this pressure. So we have merged this integral with this integral. As you can see, that it has led to the addition of this term. You will learn in thermodynamics that this is an extremely important step that we have done just now. Okay, so that is the part of the reason I'm spending a lot of time on this particular equation. So what is happening here is, now I have brought pressure work on the right hand side, and I have got E plus P by rho. Okay, P by rho, because my rho cancels out, and then I have the P times this thing that came from the left hand side. Now this 1 by rho, if you remember, at some point we had talked about specific volume. Okay, and this E plus P by rho, so specific internal energy plus P by rho or P times V, has a very important connotation. Okay, it's called enthalpy. E plus P by rho or E plus PV, if you think of this relation. Here V is the specific volume per unit mass. So that is equal to H, and H is enthalpy. Now we have not talked about these things in detail, but at least it will be useful when you do a course in propulsion or thermodynamics to think of this equation when you see the description of enthalpy. Okay, E plus PV is your enthalpy. And why is, what is this enthalpy and why is it so significant? Okay. Now let us go to the next slide. So this is a little bit of repetition of what we have seen in the previous slide. So on the left hand side, we saw that the total derivative, substantial derivative of the total energy of the system is given by the rate at which heat is added to the system. Remember, in some cases, if heat is being extracted from the system, all you do is you take Q dot to be negative. However, in most cases, your Q dot will be positive, and of course, I shouldn't say like that, because in propulsion systems, your Q dot will be positive. In case of, say, a shock wave driven post-shock region that has become extremely hot, you will have your air going into some kind of a ionization. The temperatures get very high. You might be actually radiating heat out of that system. So there your Q dot will become negative because you are giving away heat. So Q dot also has to be taken into account with the sign. W dot, by now it's the work done by the system of interest, like our fluid that is moving through the region. So work done by the system, and that comprises of shaft work, pressure work, shear force work. You saw that we brought we neglect the shear force work. Of course, you have to have proper basis for this neglect. Now, typically we end up with Q dot minus shaft work. So shaft, again, think of this as your turbine or your compressor. Then you have the pressure work. In this case, you move the pressure work into this integral, and that gives you this thing. This whole thing is known as H. Now, let us look at one or two interesting applications of this equation. So this is the energy equation in the integral form. Suppose we are looking at a steady system. So steady system means that if you have your control volume, remember I said you have to draw your control volume wisely. Okay, so let us think of control volume. Let us think of we can think of flow across a compressor. You can think of flow across a turbine. You can think of flow across your combustor, or you can think of flow through a nozzle. In case of flow through a nozzle, you are neither adding or extracting heat, neither are you doing compressor work or shaft work. So in a nozzle, what will happen is, so suppose inside, let's look at the nozzle. You can think of it as a rocket engine nozzle. Okay, so if you're wondering why are we doing nozzle here in a course in aerodynamics, just keep in mind that gas dynamics and all these things are also part of aerodynamics. So suppose this is a nozzle, and in your high-speed aerodynamics, when you study compressible flow, you will see that there is a relationship between the area ratio. So this is if you think of this as the throat, if you think of this as any other station, you will see that the area of the throat, area of any section, or rather assuming it's a sonic throat, there will be relationship of Mach number versus A by A star, etc. The contour of these nozzles, you will learn something called the method of characteristics that allows you to create nozzle contours that lead to cancellation of shock waves, so that you get a clean flow field. So some of these things are there in compressible or high-speed flow problems. There is also the concept of like choking. So if your pressure in the combustor is high enough, so we'll talk about what is stagnation pressure, what is total pressure. You can think of it at this point as pressure inside a region where my flow velocity is 0. You can have a situation where you really have flow velocity 0, say a storage tank where the flow is almost 0. On the other hand, you can think of a hypothetical situation, that is, even though there is a flow, you are thinking what will be the pressure if I bring this fluid to rest isentropically, imaginarily. But nonetheless, at this point, what I want to emphasize is, let us draw the control volume. Okay, let us draw, and as I said, your control volume is up to you, like the way you draw it, and you will see that through practice and through a lot of examples that you will work on, you will kind of learn how to draw the proper control. See, there is nothing called proper control volume, but if you draw a control volume in a certain way, sometimes you get some benefit out of it. So in this case, for example, there is, there is no Q dot, there is no compressor or turbine inside a nozzle, so there is no Q dot, no heat addition, no W dot, no shaft work. So what is happening is, so this has become 0, this has become 0. Now if we assume that the process inside this control volume is stationary in time, so what that means is, of course, your flow properties are changing as the flow is moving from the start of the combustor. So you can think of this region is the combustor. Okay, so this is where your hydrogen oxygen combustion is happening, and this is where your injectors are. Yes, so you can think of the rocket engine. So you can think of this as the injection points for hydrogen and oxygen. In the space shuttle, for example, you have liquid oxygen and gaseous hydrogen shear coaxial injectors. Several hundred of those shear coaxial injectors push liquid oxygen and gaseous hydrogen into the combustor, and the combustion ensures a certain value for P naught and T naught. So combustion creates certain value for P naught and T naught, and then downstream of this, once the combustion has happened, no further combustion is happening. I mean, see, the thing is, in the real case, some combustion is going to happen. Okay? So there will be, you will learn about things like frozen flow, equilibrium flow, non-equilibrium flow, etc. But at this point, we will assume that the combustion has happened. My gaseous charge has reached a static temperature, stagnation temperature, and stagnation pressure of T naught and P naught. And now I am expanding through the nozzle where there is no Q dot, there is no W dot. So what will happen is, and if I assume this is a stationary problem in time, what that means is, see, properties are changing along the x direction. However, if you take two pictures different in time, you will not be able to recognize which picture is at time t1, which picture is at time t2. That is known as stationary in time. So then what will happen is, this term will become 0. You understand that when you are starting your nozzle, or when you are throttling your nozzle, or perhaps when you are stopping your nozzle or your engine, this d by dt term will not be 0. Those phases will not be stationary in time. However, in most of the operation, we will see that these processes are stationary in time. So although you have these hot products of combustion flowing from left to right through the nozzle, yet so spatially things are changing, but temporally. So if you take three different pictures at three different points in time, you won't be able to say which picture came from which time point. Okay, so that is called stationary in time, or a steady state problem. So then if this becomes 0, so at this point for this nozzle problem, okay, for the compressor, flow around the compressor, flow around the turbine, flow through the combustor, things are slightly different, right? For the flow through the combustor, you will of course have a Q dot term. However, in this case, this has become 0, this has become 0, this has become 0. So now what happens? What is happening on this side? So we are saying that, so what is U dot N? So on these surfaces, my N is directed like that, limit normal outward direction. What about my this velocity vector is also directed in the same direction. You can think of these, these flows are known as quasi 1D flow. So you can, although your flow has some component in the y direction, but it is approximated as if like your flow, is just a function of x. Okay? It's known as quasi 1D flow. Quasi 1D. So although it is not 1D, okay, so here, for example, your velocity is like this, but here your velocity has a small component, because if the velocity is in the direction of the wall of the nozzle, it has some component in the y direction, but we neglect that component, saying that is small compared to the x component. Of course, this picture is not correct, because here, at least in this picture, the y component is comparable with the x component. However, in say rocket nozzles that we are looking at, the x component is way beyond being compared to the y component. So if you think of this as x, and this as y. Okay, so that's why it's called a 1D problem. It's a 1D problem. Okay, so now, so what will happen here? So it can be shown that here your velocity is like this, your surface normal is like this. So for these surfaces, this u dot n term vanishes. Similarly, for this surface, your u dot n term vanishes. So you're left with, if you think of a prime, and this surface as b prime, then you are actually left with, this is very interesting, that you are left with rho, or you can say rho a, so rho at station A times u at station A. This dA over this region will give you something like A at station A, which essentially means m dot at station A. So negative, because your u dot and your n dot are oppositely directed. So minus of this times, this is the interesting part, h at A plus u at A square by 2. So now we are neglecting this, effect of this is g and z, because first of all, you can see that they are in the same, height, although given our coordinate system is slightly different. But for aerodynamics problems, but you understand the sense of this. If this were a liquid problem, perhaps a change in z would be significant. However, here in gaseous flow problems, we will neglect this contribution from the potential energy. So then on this left hand surface, we have negative rho. So this is rho, not p. So this is rho. So rho at A, u at A times the A at A, so the cross section area at A, multiplied by h at A. So h is nothing but this E plus P by rho is h, and we are considering h at this station. So h at A plus u at A square is equal to, rather not like that. Let us first write step this plus. So again, on the left hand side we have 0. So 0, because this is 0 for this particular case. See, this is 0. This is 0. So we say 0 equals to minus this plus. Now let's work for this surface, because these two surfaces contribute nothing because of that u dot n at right angles to each other. So this becomes rho at B, u at V, cross section area at B times enthalpy at B plus u at B square by 2. It's actually a very powerful result. So if you take these things on the right side of the equation, then you can say m dot at A multiplied by H at A plus equals to m dot at B enthalpy at B plus B square by 2. So in case of the nozzle, these mass flow rates are the same. In case of a combustor, whatever is coming in may not be exactly equal to whatever is going out, because you are dumping some fuel in between. So in that case, you might write m dot A, and in that case, m dot A and m dot B will be related by, m dot B minus m dot A is equal to m dot F. Okay, in case of the combustor, but there we will have a q dot term. Okay, so keep that in mind. So we will also, quickly look at what will happen with the combustor. So then in the nozzle, what do we have? We have, because we are now able to cancel the m dots, so you can say so you see that the summation of enthalpy at station A plus the velocity square by 2 at station A is equal to this is a very powerful result. This can be written as, it's called the stagnation enthalpy. Okay, so essentially HA plus UA square by 2. So when we add the static enthalpy and add the kinetic energy, you get H naught. Okay, so H naught A is equal to H naught B. So this is a very useful relationship, and you will see that this one helps us to find the temperature and the velocity, etc., in different parts of the nozzle. And you will see that this result is widely used when we look at rocket nozzles and we try to find, given T naught, what is the velocity at the exit, etc., can be found using this particular formulation. It's very powerful use of the integral form of the energy equation. So if we next consider a situation where we are applying this thing, say for a combustor, so you can think of, let's save some space here. So let's think of this as your combustor. So this is your m dot A, so mass of air that has been sucked in, by your intake, and you have your m dot E, which is mass of exhaust. Okay, so these are slightly different from each other, but again, for simplification purpose, you can think of m dot A and m dot E to be the same, but in precise formulations, you understand that there is some m dot F that has come in. So m dot E is actually m dot A plus m dot fuel. Now, if you draw a control, so if you draw a control volume, you say that, okay, through the combustion process, I am dumping this amount of Q dot to the system. Okay, think of, this system, that drawing that we did, right? We did the, let us choose the colors properly. So we said that your control system and your control volume coincide at time t, So control volume and system coincided at time t. Then I said that after some time dt, your control volume is at the same place, but your system has moved. So this is your system at time t. So here we are now looking at, okay, so this is a bad drawing on my part. I should have actually used black color for this particular case. So here we are really looking at the control volume, okay? The control volume, the black color thing. And why are we doing that? Because the the system is moving through the control volume. So if you think of again the same thing, your your system initially was coinciding with the black lines. After some time dt, it has moved out like that. So here I'm moving from, the idea is that the substantial derivative of the total energy of the system, so the whatever is in that blue dotted line at time t plus dt, or black solid line at time t, we want to see what is the substantial derivative of that. But instead of looking at this blob that is moving, we fix our attention to that black boundary control volume, and then we run this right hand side. Yes, so what we do is we come to the right hand side. So we fix the control volume given by the black boundary here, and then we look at these things. Here again, if we think of a stationary system with respect to time, so of course shaft work is not here in the combustor, so no turbine, no compressor. We can think of a stationary system in time. There is, see, a lot of things are going on here. But what I'm saying is, if you're not throttling, or if you're not changing, or you're not having a dynamic phenomena, if you have a steady burn in the combustor, okay, not a, you're not in a combustion instability kind of situation, or flame off, or flame blowout, or some kind of flame flashback. So those things assume that in most of the flight envelope condition, we have a stationary or a steady state behavior. So we say, okay, let's this be 0 for the steady state assumption. Keep in mind, this is an assumption. Okay? If it is not a steady state, you cannot assume that. So in this case, what will happen is similar to our previous analysis. You will end up with q dot is equal to minus m dot a again. This is an approximation. Okay? We are saying that m dot f is very small. A lot of times confusion is because of authors, or whoever is describing something is not mentioning the assumptions properly. Okay? M dot is much smaller than m dot a or something. So here what you get is, you get something very interesting. Q plus H0A is equal to H0B, where Q dot by m dot A is given by this amount Q. Or in other words, you can say HOB minus HOA. So difference of stagnation enthalpy is given by the heat that is being added. And this Q is, Q dot is heat per unit time. when you divide it by mass per unit time, then Q becomes heat per mass. Okay, so we'll end up our discussion at this point, and we will continue with it in the next lecture.